All right, recording is rolling. Welcome to Thursday, March 24th. Got a slightly short class, but that's okay. I've got a PowerPoint for you guys where I'm going to hit these topics. Well, minus ideal gas law. We talked about that a few days back already. And the principles I'm going to go through today, like these principles, and we'll do a little bit of a states of matter also, are going to show up in the problems we're going to solve the few days after this. I've got a graphic for you guys. So, and this is sort of going to show up later today too. The air that we're in right now is made up of mostly which gas? Nitrogen. Nitrogen is 78% of the air that we're in right now. It's about 21% oxygen, almost 1% argon, and then trace amounts of other things. So just FYI, cool tidbits there. So because later in class today, you guys are going to see some liquid nitrogen. So let me switch the screen over. All right, and let's get going. Materials. Right, and present. Okay, materials, states of matter. Get my videos ready too. Okay. All right, so let's start with this one here, scaling, which is involved in thermal expansion, but I want you guys to know how things scale. So supposing you had some little humanoid figurine and you blew it up 3 times as big, right? Well, what exactly would that mean 3 times as big? Would it mean 3 times as tall? Would it mean 3 times the weight? Because those would actually be different things. Now, if you blow up something like any 3-dimensional object, if you blow it up bigger, it's gonna follow these exact same math that you see up here. But it's probably easier to think about a very fundamental shape like a cube. So do you guys see that the very large cube is actually composed of 27 tiny cubes? Do you guys see that? 3 by 3 by 3. There are 27 tiny cubes inside the large like crate. You guys see that? Right. So let's say you started with one of the very small cubes that has width x naught, and also height x naught, and also depth x naught, right? And I said, I want to blow it up to like 3 times the height, right? 3 times the height. Well, 3 times the height would not be 3 times the weight. It would actually be 27 times the weight. I'll show you guys why. And so if you do 3 times the height, that would also be 3 times the width and 3 times the depth. Ooh, so wouldn't that be like 27 times the volume? And since mass and weight occupy volume, that's why you have 27 times the mass and the weight. When you scale something up, again, you want to address, am I doing like 3 times the weight or am I doing 3 times the height? Because again, those are different things. Anything that's a linear property, like say like perimeter around, if you walked around the small cube and then you walked around the large cube, well, that would be a factor of 3 also. What about paint? Like if you wanted to paint the small cube and then you painted the big cube, how many times the paint would you need? Like 9 times. You guys see that? Okay, so linear factor 3. Anything that's linear is going to be scaled by factor 3. Anything that's an area, like to paint the thing, it's going to be that linear factor squared because area is some like meter squared. Anything that's related to volume is going to be that linear factor cubed. So 3 times 3 times 3 is 27. Here's that. Okay, and then mass and weight occupy volume. All right, so that's good to know. I got some videos that aren't playing, but I'll pull them up over here. Okay, let's do scaling real fast.
You got a drink, you want to cool it. Someone says, put an ice cube. Someone else says, no, crush the ice cube up, then put it in. It'll make the drink cold faster if you crush it up. Someone else say, it's the same amount of ice either way. Make no difference. You say, where's the next?
Oh, what do you guys say? Do you guys see this cube behind him on the board? Looks very similar to the graphic head on that slide. Okay. Suppose that represents one very large block of ice, right? And you throw that in a cup to cool down the liquid. Okay? And then you say, well, hey, well, what if I went back and I chopped it into like 27 small cubes and then threw those 27 small cubes inside the liquid? Which is going to cool down that liquid faster, the one single block or the 27 small cubes? What do you guys say? The small cubes. Crush it up to cool down faster. Right? Now, why? Because the crushed up cubes have more combined what? Surface area. Yeah, and that surface area has to do with that thermal conduction. Right? There's Newton's law of cooling that I haven't written down for you guys, but the rate that this temperature change happens is proportional to the surface area that this happens. Right? So he talks about the rest of this. He goes through some examples of what if you have, for example, a big old potato. I'm gonna bake this potato and it takes like a whole hour to bake it. But what if you cut it into little skinny French fries? Wouldn't that cook faster because they have more surface area? So pretty good enough. Let's do, okay, this one right here. So keep on the idea of like expansion, or so thermal expansion in this case. You guys know that most materials, if you heat them, they expand. There's a few exceptions to that, but most things, including metals, you heat them, they expand. I'm interested in this metal ring. Let's say that you're heating it uniformly. So we're increasing the temperature the same all the way around the ring. Okay, that's going to cause the material itself to occupy more volume. That would be true, right? I'm interested in the size of this hole in the middle. Let me see, show of hands. I'll give you guys 3 options what could happen to this hole. The hole itself might shrink smaller, the hole might get bigger along with the ring, or the hole might stay the same size as you heat the ring itself uniformly. Show of hands, how many guys say the hole inside gets smaller? Who says that? Who says the hole inside gets bigger? And does anybody say the hole stays the same size? Ooh, okay, so we got some votes on each one of those. Let's check this out.
See, right now, it goes through. With a little
Fairly,
effort, it goes through, yeah?
fairly goes through.
I'm not gonna take the time to heat up the ball. I'd waste your time, because you know the ball would get bigger and no way it would go through. I'm gonna heat instead the ring. Get that ring nice and hot. Is the ring expanding? Yeah, it's expanding. How about the hole? The hole expanding? See, a lot of people think this. A lot of people reason that the hole is it's gonna expand this way and expand in this way because the ring's gonna get fatter. Will that ring get fatter? Turns out it will. So they think this part will expand out here, and this part in here, and the hole gets smaller. But lo and behold, appreciably bigger. So the hole does get bigger again. If we take our ring and we cut it up into 4 pieces, gang, 4 pieces. And if I put even any one of those pieces on the oven, would it get bigger? Would it expand and maybe look like this? No way. It's going to expand and look like that. And this side here is longer in an expanded state than like this. So take them apart and look at it, and you can kind of see it. Or take your ring and open it up like this. Is it going to get fatter? Yes, it's going to get fatter. So it expands out to here maybe, yeah? But that's not the end of the story. You see, we're so busy thinking about what happens like this, huh? That we forget it's expanding this way too. And it expands lengthwise as well. And lengthwise, we see it expands out to here. And I submit to you that this dotted line on the top is longer than this solid line below. Hi, gang, thermal expansion time. Here I have what's called the bimetallic strip. It's a strip of metal consisting of 2 kinds, brass on one side, steel on the other, welded together. I'm going to heat it up. Looks like it's bending. It's bending because one side's expanding more than the other. If I take this and turn it into a coil and heat it up, it would shrink. Or cool it, it would expand. That would be a thermostat. Hey, let's talk about this expansion and this expansion under different temperatures and everything. We got something here that's kind of neat today. Ted, could you give me a hand?
It's got here some liquid nitrogen. Now, I just showed you guys that 78% of the air that we're in right now is nitrogen. So imagine how crazy cold you have to get it to liquefy the air in this room. That's what they have there in that bottle.
Almost 80 degrees above the absolute 0 temperature.
Ooh.
Now, can we have a volunteer jam their hand in there for about 5 minutes? Okay, nobody gonna do that, right? Okay, let's show how the let's show how the volume of something will change. Here's an air-filled balloon, gang. Okay, what's going to happen to the volume when it gets cold? How many say, oh, it's going to expand?
Let's remember ideal gas
Stand
law.
up. And what happens to the volume, gang?
Ideal gas law. Decrease the pressure, decrease the temperature, that'll decrease the volume.
Look at that. Now it's going to start to warm up to air temperature. What happened to the volume? What happened to the volume? We bring it above air temperature.
It expands, it blows up.
Let's try the flour.
There's a flower Chet found out in the ground. It's kind of nice and limp, right? Kind of limp, isn't it? Okay. What happens if we slow those molecules down? Yeah, why did it fizzle like that? What's going on? Oh, gang, did you see such a thing?
Oh. All right, next thing. Archimedes principle. Okay, so gonna walk you guys through this. This is buoyancy, right? And then you'll get to see Paul Hewitt also do the experiment that you guys are seeing right here. Right, so when you jump in the pool, you guys know that there's a buoyant force, an upward force that lets you float. Now, two things. Why does the buoyant force specifically, why is it directed upward? Why does it force you upward? And furthermore, can you quantify it? Like how many newtons of force would that represent? Right, so one at a time here. First of all, why is the buoyant force upward? Well, it has to do with the fact that objects are three-dimensional and that the deeper you go, the more pressure there is. Right? You guys know that. You jump in a pool in the deep end, the deeper you go, you feel more and more pressure building up. And in fact, that pressure is directly proportional to the depth that you dive. The pressure is equal to rho GH, where rho is the density of the water, G is the gravity field, and H is how deep down you dive. So if you dive twice as deep, you get twice the pressure. Okay. And pressure, by the way, always pushes perpendicular to the surface that it's pushing against. Okay? So on the sides, you got pushing to the right, pushing to the left, that cancels out. That's why there's no net force. That's why the buoyant force doesn't push you right or left, right? But well, why vertically though, right? Well, there's some pressure on the bottom pushing up, and there's some pressure on the top pushing down. But you guys know the deeper you are, the more the pressure. So there's more pressure from the bottom than the top. Pressure times area turns back into a force, buoyant force. That's why the direction of the force is upward. Okay, now how can you quantify how many newtons of force? Well, turns out that, and this is what Archimedes figured out thousands of years ago, that that buoyant force is equivalent to the weight of the displaced fluid, right? So the weight of the displaced, maybe water in this case, right? And you can see that with the numbers they have marked up here. So maybe this weight weighs 4 newtons. So 4 newtons of weight just hanging in the air, right? And then we're going to dunk that in the water. And you see that there's a buoyant force of 3 newtons, right? Because now there's only 1 newton of tension in the string. So what's holding this block up? If you made it free by a diagram, there'd still be 4 newtons of gravity weight down, but there's 2 forces upward. The tension force in the string, 1 newton, plus 3 newtons of buoyant force, right? Holding this in place. Now, do you guys see that weight is now occupying space in the water? Well, how much water is that? Well, if you capture all that water, the weight of that water also ends up being exactly what that buoyant force is. That's what Archimedes' principle says, is that the magnitude of that buoyant force is equal to the weight of that displaced fluid. Anything that floats above water has to have a density that's less than the density of water, because it's the volume that it occupies down below the water is occupying a volume of water whose weight would be equivalent to the weight of the entire object to make it float. Okay. All right, let's get more granular though. Let's go from that first line to the second line. Okay. You guys know that weight is equal to mass times gravity field. Right? You guys have seen that since forever in this class. But isn't mass equal to density times volume? Because density is mass per volume. So mass is density times volume. So let's do that. Let's break mass into density times volume. And that's what this is here. Density of fluid times the volume of that displaced fluid. Density of the fluid times the volume of that displaced fluid gets you back to the mass of the displaced fluid. Multiply that by gravity field. That brings you back to the weight of the displaced fluid. And so rho GV, but the rho, the density we're talking about, is the density of the surrounding fluid. Okay, but multiply those together, you get the buoyant force. Okay? You guys kind of got that? Okay. We're going to apply this to certain problems in the future, including this one. On that printed page that you guys have had for a few days, we're eventually going to solve this one here, the iceberg question. Well, what percent of an iceberg is either submerged or above the surface, depending on how you frame the question? Do you think it has to do with the densities of those materials? Right? Like if the density of ice happened to be more than liquid water, it would just sink to the bottom always, right? But anything that has a density less than water will float. And the less density it has, the more it will float above the surface. So what about an iceberg? This is going to be the first step. The first step is this here free body diagram. There are 2 forces acting on that iceberg. there's the weight acting down, and there's a buoyant force acting upward. Now you guys know weight acting down is mass of the ice times gravity field. Okay? But the buoyant force up is equal to, well, the weight of the water being displaced. That's density of the surrounding fluid, density of the water, liquid water, right, times gravity field times the volume that's displaced, which only accounts for the submerged part of the iceberg. Right? And then we'll set up that equation and then solve for stuff from there. So that's the first step. I do want to make a side note about this because I was trying to find a good picture of an iceberg. No, this is just an obviously hand-drawn iceberg. Somebody just drew this, right? Interestingly, I could not find a sort of a realistic orientation of an iceberg because this is not actually stable. This would fall over on its side. You guys remember studying stability last semester? For some reason, everybody always draws icebergs like this in an unstable position. I don't know why. There's just a side thought. Okay, let's move on to Pascal's principle. We just did Archimedes' principle. Let's talk about Pascal's principle. And so Pascal's principle says this: pressure is transmitted without loss throughout a container. Maybe that would be especially true for gases, but here's sort of the liquid version of that, is that I might say there are equal pressures at equal depths. So you guys are looking at a hydraulic lift, right? Like a hydraulic press, hydraulic lift. Okay. And well, you see what's going on is that there's some very small input force that's lifting a very large weight on the other side. Right? How's that working? Let's start with Pascal's principle and I'll let you guys step through step how this works. Okay? And then again, you guys are going to solve some problems related to this in the future, near future. So do you guys think that the bottom of this container, there's equal pressure all along the bottom, right? Whatever this fluid is, maybe some oil, maybe it's water, right? The equal pressure all along the bottom, right? Equal pressure. What about this level right here? Is there equal pressure all along this elevation? Yeah. What about when you get up into the piston area? Do you think this pressure right here is equal to this pressure right here? Yeah, also the same. So equal pressures for equal elevations. That's or equal depths, right? That's what Pascal's principle says. Right now, okay. So the pressure on the left side is equal to the pressure on the right side. Say pushing up against these pistons. Now you guys know that pressure is force per unit area. That goes back several months ago in this class, right? Newtons per square meter, some number of pascals of pressure. Right? And since the pressures are equal on both sides, right? So got that. If you rearrange this equation, though, you can get one that looks more like this. The corresponding force is pressure times area, right? If you just rearrange that, force is equal to pressure times area, right? And since the pressure is the same on both sides, but the cross-sectional area that is pushing against is different, then you get different resulting forces. So some pressure times a very large area will result in a very large force. Ah, you guys see that? Right? And then pressure times a small cross-sectional area results in a small force. Now they're showing a downward force on the left side and an upward force on the right side, but really each of those red vectors, red force vectors, has an equal and opposite Newton's third law vector too, right? Like the car weighs a bunch, and then there is pressure on the left side. It's also pushing up against the piston, right? So equal and opposite forces, but you guys get the idea. So a small input force on the left side results in a very large output force on the right side. You guys get that? Okay, so that's Pascal's principle. Hold on to that idea. We'll be solving problems with that later. Now let's go to a third principle, Bernoulli principle. So we did Archimedes' principle, then we just did Pascal's principle. Now let's do Bernoulli principle. Bernoulli's principle has to do with fluids in motion. What happens to the internal pressure? Let me start with the end result, and then I'll go back and explain it. Now, this is kind of a long process, but let me start with the end result. You guys see the Venturi effect over here? Right? There are two pictures that show that. Let me focus on the top picture because it's an actual photograph, which is a little bit more scientific, right? So it looks like I have two different fluids in here. Maybe the top is some kind of oil and the bottom is some kind of maybe water, or I don't know, maybe the top is water and the bottom is mercury. Let me go with that story just to pick a story. So I'll go with water and mercury. Let's just, for sake of argument, right? And let's say that the water is flowing. Now they should have it flowing right to left, but the direction really doesn't matter because the end result would be the exact same as long as the water is flowing, right? As long as it has some kind of motion, right? Why does that result in some pressure differential? Why would that be? Let's see. Well, I do see that there's some change in the pipe size, say going from a large pipe to a small pipe. So maybe something to do with that. Okay. Why would there be a pressure change? Okay, good. Let me do a live demo for you guys that also shows the same end result, and then we'll go back and see why. Right. So I've got a paper here. Right. I'll hold this paper just kind of like this. I'm going to blow a stream of air over the top. Let's say a stream of fluid, maybe like moving fluid. Now, when I do that, is that going to push the paper down, or is it going to vacuum it up? What do you guys think? How many of you guys think that if I blow a stream of air over the top, it's going to push the paper down? Who thinks that? Who thinks it's going to vacuum it up? Vacuum it up. Oh, I see a bunch of hands. All right, you guys are following. Yeah, let's test this out. Do some real science here. Yeah, it sure does. In fact, if you got some paper on your desk, you can try that out too. It sure does vacuum it up. That's interesting. Why is it then that a moving fluid results in a decreased pressure? Well, all right, so back up to the slide. So a good starting point for that, I have to explain something else first, which is conservation of flow. Right. So if you have a pipe system and a fluid is moving through, especially if the fluid is a liquid, like an incompressible liquid, that's especially true for conservation of flow, which is that the flow rate is the same everywhere in the pipe system, like the gallons per minute. The gallons per minute going through the large pipe is the same gallons per minute that's going through the small pipe, right? Same volume per time, right? Or in the metric system, you might say cubic meters per second is the same everywhere, okay? Now, cubic meters per second, you could break down in kind of a funny way. You could do cross-sectional area multiplied by the speed of the fluid moving through, because wouldn't that be square meters multiplied by meters per second, right? Wouldn't that be true? Oh, that would be cubic meters per second. And that has to be conserved because that's the same everywhere, especially for uncompressed fluid, right? Okay, so one way you can interpret this conservation of flow then is that if you have water moving through a large cross-sectional area multiplied by a slow speed, that's equivalent to a small cross-sectional area multiplied by a fast speed, right? That's to say that when, going up to this picture now, when the water goes from the big pipe into the little part of the pipe, it has to speed up, Okay, is that okay? That checks out, has to speed up. Kind of like blowing a stream of air, speed up fluid, right? Okay, now let's go to the very top equation. You guys see this very top equation here? Does that almost look like conservation of energy from a few months back? Conservation of energy. You guys remember some energy plus 1/2 mv squared plus mgh, right? Kinetic energy, potential energy, the whole deal, right? Equates to some energy plus 1/2 mv squared plus mgh somewhere down the line, a different time in this system, right? It's conserved. That's why you can say equals, because energy is conserved for a closed system. Okay, we got that. Now, if you take that conservation of energy and you divide by volume, see what it says right here? Energy per unit volume. Energy per volume turns out to give you units of pascals, which is like a pressure unit, right? And what about this term? 1/2 mv squared divided by volume. Oh, mass divided by volume. Hey, isn't that this here? Rho, density, and mgh. Well, m divided by v is also density. So we get 1/2 density v squared plus density times gh, right? You guys said. Okay, so this is conservation of energy, but just in terms of pressure units, isn't it? And that's what Bernoulli principle is. Now, let's go to the next step of why does this explain why a moving fluid results in a decreased pressure? Right? So I see 6 terms here. Right? Boink, 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 boink. These guys counting 6 terms. Okay. Now to pair it up with this picture right here, we can actually simplify that down to 4 terms. I don't see a height change. Do you guys see how this is just a horizontal pipe system? Okay. You guys know the deeper you go down in water, the more the pressure increases. So let's just stick to a horizontal system, which means I'm going to get rid of this term and this term. I mean, if H1 is equal to H2, then these would just cancel out anyway. Is that okay? So that simplifies to just boink, boink is equal to boink, boink, right? Just these 2 terms added together equals these 2 terms added together. Is that okay? Okay. Okay. So and remember too that at the large cross-sectional area, it's moving very slow. And at the crimp in the pipe, it's moving very fast. Okay, so this V2 is very large compared to this V1, just like it says right here. V2 is greater than V1. It has to speed up, go through the skinny part. Okay? And if that's true, if you started to tag number seeds, let's say this is an internal pressure. Like if you're a fish swimming around, you feel some pressure on you, right? And that's how you can interpret this P1. It's like an internal pressure in that fluid in that system. Okay? Let's say this is like 100 units and this here is like 20 units, right? But V2, the fact it's bigger than V1, this might bump it up to like 30 units, which means that P2 has to decrease to like 90 units. So 100 plus 20 is equal to 90 plus 30, right? You guys get that? Okay, so let's go back to our fish story. If there's a fish swimming around, right, then right here, the fish would perceive a high pressure. And by the time he gets to this crimp in the pipe, he perceives a low pressure, exactly what it says right here in red. pressure 2 is less than pressure 1. Okay, guys get that? One classic example application of Bernoulli principle is what makes a plane fly, right? How do you lift like a several ton plane and have it fly through the air? I still think that's amazing to this day. Well, part of it has to do with Bernoulli principle. So if you shape the wing so that there's more surface area on top of the wing than on the bottom of the wing, then as the plane is flying through the air has a longer distance to flow over the top than the bottom. Therefore, it has to move faster over the top than the bottom. Therefore, there's a decreased pressure on the top compared to the bottom. So that results in lift, right? There's a net upward force. Right? The other reason that planes fly is because you actually tilt the wing so that as the plane is moving through the sky, that also helps give it some lift. Okay? So there you go. There's Bernoulli principle. Right. Cavitation. You know what? I need to go back a slide to explain cavitation. Do you guys remember reduced pressure boiling? You guys see this graphic right here, this P versus V diagram in different states of matter? There's two ways to make water boil. One is to throw it on the stove and increase the temperature, but the other way was to put water in a vacuum chamber and decrease the pressure. Remember, water starts boiling with decreased pressure. Okay. So let's take a look at this. Suppose you're an engineer one day, you're designing a pipe system for some city, and you're imagining, okay, I got big pipes and little pipes, and they're all connected together, and this flows into this, right? Well, if your small pipe is too small and the water flowing through it is too fast, and that decreases the pressure too much, do you think that you could get to a point where the water actually starts to boil inside your pipe system? And do you think that would be really bad news? That would be. There's a term for that. It's called cavitation. And that can ruin your pipe system. And if you have a pump, that can oftentimes ruin a pump. And there you go. There's a ruined pump due to cavitation. Right? You got a crimp in the pipe system, water starts boiling, creates all these, cavitation pits. So yeah. All right. And finally, let's look at states of matter. I know we've been looking at phase changes, but so here's your main three states of matter at room temperature: solid, liquid, gas. You guys know what those are. Liquids and gases are both considered to be fluids. The physical difference between those two is liquids are generally not compressible and gases are. This is, say, if you have an air-filled balloon, air-filled, that's like made of gases, right? And you compress it, its volume will change. But if that balloon was filled with water and you compress it, its volume does not change, right? Okay, so that's the main difference between those two. Now, if you keep heating a gas, it will undergo a process called ionization, where the electrons strip away from the positive charged nuclei that they surround, and you'll get a new state of matter called a plasma. Let's look at some examples of some plasmas here. Plasma. You can create plasma at home with a grape and a microwave oven. So what you do is you take a grape and you split it and take the two halves of the grape and leave them in contact with each other and put this in the microwave. Now notice they took out the turntable, right? So there's no turntable. Right? You want to get rid of that. And you throw a glass over this. Now, why does this create plasma? Well, because it turns out that the diameter of that grape is a factor of the wavelength of the microwave that's being sent across your microwave oven. So that means it'll set up a standing wave, which amplifies the energy. You guys remember how that works? And then you can get an ionized grape and get a little plasma ball right there. All right.
Mr. Griffin,
Oh, yeah.
would we be able to do that at home, or would it explode our microwave?
I'm not gonna make a recommendation,
Fair enough.
but it's on the internet.
Everything's true on the internet.
Yeah, I got the video version for you guys. Maybe ask your parents about that one and say, that's what Mr. Griffin showed me. Yeah, trying to blow up the world. All right, so examples of plasma. You guys got lightning, northern lights, stars. Fluorescent lights. When I hit the on switch right here, actually these bulbs right here work on not incandescent lights, but fluorescent lights. That is true. It's ionized gas inside those bulbs. Or if you get those ice cream looking lights, same thing. That's ionized gas. Neon lights, plasma TVs, plasma ball. Those are all examples of plasma. Now, okay, there's plasma diagram. So ionized, right? Okay. What's the technology application of plasma?
With a gas flowing through the chamber, plasma can take on many rich colors. In the vacuum chamber, you can see argon gas emitting purple light. Nitrogen emits a reddish orange light. And fluorocarbon emits blue. All of these different colors are specific to the gas chemistries. Plasmas can be used as a controllable reactive gas. So for example, if we put an object at the edge of the plasma, the charged particles will bombard the object, etching away at the surface. The electronics industry has used this concept to make smaller and smaller patterns into silicon, which is used in laptop computers, cell phones, and a whole wide variety of other applications. Plasma processing proved essential to the rapid miniaturization and increased performance of computers. These plasma processes are integral to the information revolution.
Yay. All right. Now, there are more states of matter even than just these four. Also, sometimes I've seen, say, if you heat a plasma even crazy hot enough, you can change the structure of those atoms, like rip apart the atoms themselves. Right? Let's go the other way. What if you cool a solid near absolute zero? Now, if you get it too cold, then the internal structure of the atom also collapses on itself and creates a very strange state of matter called Bose-Einstein condensate.
It would not be a solid, or liquid, or gas. It was given a name almost as strange as its properties, a Bose-Einstein condensate. For the next 70 years, people could only dream about making such a condensate.
Matter can exist in various states. Atoms at high temperature always form gases. If you cool the gas, it becomes a liquid. If you cool the liquid, it becomes a solid. But under certain circumstances, if you cool atoms far enough to extremely low temperatures, they undergo a very strange transformation. They undergo an identity crisis. So let me show you what I mean by an identity crisis. When you go to low temperatures, the quantum mechanical properties of the atoms become important. These are very strange, very unfamiliar to us. But in fact, each one of these atoms starts to display wave-like properties. So instead of points like that, you have little wave packets like that moving around. It's really difficult for me to explain just why that is, but that's the way it is. Now, as you go to very low temperatures, the size of these packets gets longer and longer and longer. And then suddenly, if you get them cold enough, they start overlapping. And when they overlap, the system behaves not like individual particles, but particles which have lost their identity. They all think they're everywhere. This little wave packet over here can't tell whether it's this one or that one or that one or that one or that one or there.
All right, that guy's going crazy. All right, so when we get to quantum mechanics, well, what you guys see is that things don't exist in like particles. Things that actually exist in probability curves, like probability waves. So there's like a size distribution of existence. Okay, now, have people created Bose-Einstein condensate in the 1990s?
June the 5th, 1995, turned out to be a big day in the history of physics. They had finally made what Einstein had predicted 70 years before, a Bose-Einstein condensate.
Our first reaction was, wait, we got to be careful here. Let's think of all the different knobs we can turn, checks we can make, and so on, to see if this really is Bose-Einstein condensation.
A condensate is sort of like a vampire. If the sunlight even once falls on it, it's dead. And so its realm is the realm of the dark. But we can take pictures of them because we strobe the laser light really fast. And even as the condensate's dying, it casts a shadow, and the shadow is frozen in the film.
Wyman and Cornell created the first Bose-Einstein condensate in a cloud of just 3,000 atoms of rubidium, the first in the universe, as far as we know.
As far as we know. Actually, when you get down to crazy cold temperatures, some other strange quantum mechanical properties will take over. You can get superconductivity that's like zero electrical resistance, which is like crazy. And also you can create a superfluid that has like zero resistance to much. Here, show you guys a superfluid. This will be the last one we look at today.
Superfluid.
There were more surprises ahead. In the 1930s, another strange phenomenon was observed at even lower temperatures. This rapidly evaporating liquid helium cools until at 2 degrees above absolute zero, a dramatic transformation takes place.
Suddenly, you see that the bubbling stops and that the surface of the liquid helium is completely still. The temperature is actually being lowered even further now, but nothing particularly is happening. Well, this is really one of the great phenomenon in 20th century physics.
The liquid helium had turned into a superfluid, which displays some really odd properties.
Here I have a beaker with an unglazed ceramic bottom of ultrafine porosity.
Ordinarily, this container with tiny pores can hold liquid helium. But the moment the helium turns superfluid, it leaks through.
We call this kind of flow a superflow.
Superfluid helium can do things we might have believed impossible. It appears to defy gravity. A thin film can climb walls and escape its container. This is because a superfluid has zero viscosity. It can even produce a frictionless fountain, one that never stops flowing. Superfluidity and superconductivity were baffling concepts for scientists. New radical theories were needed to explain them.
All right, and that is our pause point today.